So in the last lesson, we saw that when light changes material, it bends. And we looked at whether it bent towards the normal or away from the normal. Bends towards the normal when the light ray is slowing down, and it bends away from the normal when the light ray is slowing up. It's speeding up, I should say. Now we're going to get a little bit more quantitative with it and look at something that we call Snell's law. Snell's the name of a person who came up with this law hundreds of years ago. And so I'll just state what the law is, and then we'll get back to what it actually means. The ratio, the indexes, or the indices of refraction, when light travels between two materials, is equal to the inverse of the ratios of the sine of their angles of travel. So we'll get back to the details about this first, or eventually. What I want to do first is look at what this whole idea of sine. What is sine? Now, if you are fortunate enough to have already taken grade 10 math, then this should be review for you. In fact, if you're pretty certain that you not just that you can calculate what a sine is, and you can use your calculator properly to do sines and inverse sines and things like that, then just move forward until we're on to the next slide, because you don't need to see this. But depending on which semester you're taking math compared to science, or what your background in math looked like, then the next few minutes might be beneficial to you. So what is a sine? So it all has to do with right angle triangles. So I've got a couple of right angle triangles here, and so there's a little symbol for a right angle. So let's assume that our triangles have a particular angle, and I'm going to call that one there theta. And they both have the same theta. And if they're both right angle and one of the angles is the same, then it means that the other angle is the same as well. And if we have any triangle with three identical angles, then we say those triangles are similar. And in any similar triangle, the ratio of the sides of the similar sides are the same. So what we're going to look at now is labeling sides. So the angle I'm concerned about here is theta. Every triangle has three sides, and we're going to give them three names. This one you already know. This one is the hypotenuse. Just give it a symbol of H. The side opposite to our angle. Well, if it's opposite to the angle, then we'll just call it the opposite side, or O. And this side, the side that's next to or adjacent to the angle, we're going to call the adjacent side, or A. So same thing with this triangle here, a different hypotenuse, because it's a much larger triangle, and this is a different adjacent side, and this is a different opposite side. So the idea of the sine is that when we look at a very specific ratio, so for a triangle with this given angle theta, we say the sine, and the short form is just sin, of theta is the ratio of the opposite side to the hypotenuse. So it's the ratio that you get when you divide the length of the opposite side by the length of the hypotenuse. And it doesn't matter how big your triangle is. If the angle is the same, so if I have a triangle like this, I have a 30-degree triangle, and I say this side is 10 meters long, we'll say. Then the side, and this side, we'll just call it y. We want to try to figure out what y is. Then we would say the sine of 30 degrees is equal to y over 10. And if we multiply both sides by 10, we would get 10 sine 30 equals y. So how do you plug this into your calculator? Really depends on what calculator you have. what I would suggest that you do is just do this part first. Now, if you do this properly in your calculator, there's a sine button on your calculator if you have a good calculator. If not, you're going to need one. Find the sine button on your calculator, or sin, and press that button after you've typed in the number 30. So most calculators are going to do that. Other calculators might have to put sine 30 and then press enter. Either way, that should give you 0.5 for this particular case. If it doesn't, then you'll want to figure out what's going on. There are a bunch of things that you could be doing. For example, not having your calculator in degree mode. And if it's not giving you that, then you're going to want to check with somebody, check with your teacher, check with a friend, figure out what it is that's not going right. So 10 times 0.5 is y. So that sine of 30 degrees means that the opposite side is always going to be half, or 0.5, of the hypotenuse. And so y, in this case, is 5 meters. Now, if I have a larger triangle, and let's say that I have a triangle and this is 50 meters. So it's a way larger triangle. If that angle is still 30 degrees, then the ratio of y over 50 is still going to be the same as the ratio on the first triangle of y over 10. So that ratio, sine of 30, is 0.5. So in this case, y would be equal to 25 meters. All you really need to know in this course is how to plug in sines of angles. And one other thing, let's say we have something like this. And this side here is 2 meters and this side here is 10 meters. And we want to know what angle that is. Now we're going the other way around and it gets a little bit tougher. But we still have the same kind of, we say the sine of our angle. Well, we don't know our angle, so we'll just call it theta. Sine theta equals the opposite side, so that's this side, 2 over the hypotenuse, which is that side, 10. So we get sine theta equals 2 over 10, which is 0.2. So how do we go about getting that? In this case, what you're going to want to do is an inverse sine. So we say theta equals sine -1 inverse sine of 0.2. And again, how you plug that in really does depend on your calculator. And the one I'm doing here, I'm typing in 0.2. And usually it means you're pressing like shift sine or second function sine or something like that. And right here I made a little mistake because I haven't calculated in the wrong degree, so I'm going to put it in degrees. I'm going to try it again. I'm going to 0.2 and I'm going to press second function sine, which really is going to give me the inverse sine. And that's going to give me 11, we'll call it 11.5. Maybe we'll just keep everything to degrees in this course, and we'll go 12 degrees. So for a triangle with an opposite side of 2 meters and a hypotenuse of 10 meters, the angle will be 12 degrees. So that's just a matter of knowing how to plug in your sines and your inverse sines. We'll save the details about the other ratios, like your cosine and your tangent, for your math course. So let's go back here. In fact, maybe what we'll do is come back to this, highlight that part, let's group that, and copy it and bring it over to the next page. You don't need to do that, but I just want to make reference to it as I'm just going to put it right down here. So let's look at what this says. So we have a light ray traveling from one substance, which has a specific index of refraction. We'll call it n with the subscript 1. Again, if you're using computers, if you're using Google Docs or whatever, learn how to use the subscripts. You'll need them. And this substance here is, we'll call that N2. So let's say that we have a light ray, change the color here, I have a light ray coming in, and it hits that spot, and then it's going to bend, and it's going to bend like that. And I'm going to put my normal in. Remember, the normal comes 90 degrees to the surface, So there's the normal. As we're going to see, it doesn't really matter which direction the light is going for. We'll just arbitrarily say that it's that way. So the ratio, the indexes of refraction. So the ratio of n1 to n2. Ratio is like a fraction, so n1 to n2. When light travels between two materials, so that's what's happening here, is equal to the inverse of the sines of their angles. So this angle here, we'll just call this theta 1. Whether it's incidence or refraction, we don't really care. And we'll call this theta 2. So the inverse means that we're going to flip it. This time we're going to have the 2 on the top and the 1 on the bottom. So it's equal to, we're going to have the sine of theta 2 over the sine of theta 1. So inverse is that we flip the 1 and 2 around, and we took the sines of each of those angles. So this, in a nutshell, is what Snell's law is. We like to rearrange it in a nicer form. So what we're going to do is we're going to multiply both sides by sine theta 1. Ran out of room a little bit there. And we're also going to multiply, well, let's do that first. n1 sine theta 1 over n2 equals, that's going to cancel with that, and so that's just going to leave us with sine theta 2. And now we're going to multiply both sides by n2. Multiply by sine theta 1 there. Multiply both sides by n2. And those n2s are going to cancel. And what we end up with is n1 sine theta 1 equals n2 sine theta 2. So you don't need to worry about being able to derive this. It is possible. You need a little bit of geometry, and you need to use wavelengths and frequencies and things like that. You actually do have enough knowledge at this point to be able to derive this equation. I don't think I would expect it. When this was a grade 11 physics material, then I might have expected some of the more students that like to challenge themselves a little bit more to take a shot at this. If you want to, then go for it. I think it'd be a great little exercise, but it's not an easy one to do. So don't worry about how to go about it. Just understand that this is Snell's law, and I'm going to want to make sure that you can use it. As I've said on multiple occasions, I don't want my carpenter to memorize 50 different kinds of hammers or 18 different kinds of nails, but I would certainly want to make sure that they're using the right hammer and nail when they can actually do something with it. So let's take a look at doing something with it. So here's an example. So we've got a diamond resting in a cup of liquid for some reason. Light ray hits the surface of the diamond at an angle of 40 degrees from the normal and refracts at an angle of 20 degrees from the normal. So we want to know, we get the index refraction of that liquid. Now, just because it's liquid doesn't mean it's water. So you don't need to get really fancy. You don't need to draw a cup in the liquid and a fancy shaped diamond. All you have to do in your diagram, you really should have a diagram, is say, all right, so here's my diamond, and we'll call that N1 is 2.42. How do you know that? You look it up. You have a chart. You go back to, the last lesson. You go back to your textbook. You go to the internet. You find it on a test. You'd be given any of that information that you need. The only one that I wouldn't normally give you is air, where n equals 1. And then you have liquid, the unknown liquid, where n, we'll call that N2, and we'll just call that n. We'll just say we don't know what that is, so we'll just call it n. We could have called it x or whatever. So the light ray is coming in at an angle of incidence of 40 degrees from the normal. You always assume, unless you're told otherwise, if it says angle of incidence, then that is measured from the normal. You will probably encounter questions where it's giving you the angle from the surface. If it did give you this angle right in here, you just have to take that number and subtract it from 90 to figure out what your angle from the normal actually is. And then you're told that it bends that way because this number here is only 20 degrees. So it's bending towards the normal, which tells you that the material, the liquid, is light's traveling slower, which means that it's going to be a considerably high index of refraction. So then you can check your numbers. So Snell's law gives you n1 sine theta 1 equals n2 sine theta 2. Plug your numbers in. So 2.42 times the sine of 40 degrees equals n2, or I guess we just called that n. So n sine of 20 degrees. So a couple of different ways you can do this. I would say slow it down is slow and steady wins the race. So you go 2.42 times 40 sine on your calculator and press the equal button, and that gives you 1.5555. So 1.556 we'll say equals n times the sine of 20. So I just plug 20 sine into my calculator. It gives me 0.342. And so to get n, I take the 1.556 divided by 0.342. And that gives me an index of refraction of a whopping 4.55. And that's huge. So I don't know if this actually exists, but with these made up numbers, you'd have a really, really large index of refraction. The second question that we have here, a laser beam enters water at an angle of 30 degrees from the surface. What is the angle of refraction? So if you're not told what the other substance is, I think it's fair to assume that unless you're being asked to solve for it, like we were in the last question, if we don't know anything about it, but we need to know something about it, you can just assume that it's air. So it's entering water, it's probably entering water from the air. So let's say we've got air here, where n equals 1. Again, that's the only index of refraction that I would say that you should know. And then we have water here, and n equals 1.33, and again, you can look that up. And read your question really carefully. The light ray comes in here at 30 degrees to the surface. But remember, and it's going to bend, and we know with water it's going to bend towards the normal. So there's our normal. So when we're writing down what theta 1 and theta 2 are, well, theta 2 is what we're trying to calculate. I'll just call it theta. And theta 1, we're kind of given, but we actually have to do a little intermediate step, because this whole thing from the surface to the normal is 90 degrees, and we're given the angle of 30 degrees from the surface, which means the rest of it must be 90 minus 30, or 60 degrees. So theta 1 is 60 degrees. So now we can go back and put n1 sine theta 1 equals n2 sine theta 2. And so that's 1 times the sine of 60 equals 1.33 times the sine of theta. Now the sine of 60 is about 0.866. Multiply that by 1, it doesn't change it. Equals 1.33 sine theta. Divide each side by 1.33. So you get 0.866 divided by 1.33, and you end up with 0.65, or say 651, equals sine theta 1. So in order to get theta, you need to take the inverse sine of that 0.651, and that will give you what theta is. So you take that 0.651, press second function, sine on your calculator or something to that effect. Again, you will need to know your calculator for your test, which means that when you're writing a test or you're doing your exam and you're doing questions like these, it really helps to have your own calculator. So be proactive and make sure that you have your own calculator and you know how to use it. And it turns out that this angle is about 40.6, so we'll call it 41 degrees. So the angle of refraction here, theta 2, is about 41 degrees. So check out the textbook questions included here or given by your teacher in order to practice some of these questions. They're pretty simple to do. You just have to have a little bit of practice before you get really, really good at them.